Substitution. The substitution method for antidifferentiation enables us to rewrite the integrand into a form that makes it easier to antidifferentiate. Each differentiation rule has a corresponding integration rule. Substitution refers back to the chain rule, which is used when we have a composite of functions. For example, if we were to differentiate the composite function f of g of x, we would take the derivative of f, evaluated at g of x, times the derivative of g of x, the derivative of the outer function, if you will, times the derivative of the inner function, kind of the slang way of verbalizing it. So that if I took a look at the derivative of x squared plus 1 to the 10th, in my mind, I'm seeing the derivative with respect to x of u to the 10th. How do I differentiate it? Well, I take 10 u to the 9th and times the derivative of u. That's what we're seeing right here on this line. Now you know this already. And you know that the inner function is x squared plus 1. What I want to do is think in terms of antidifferentiating. So if I simply integrate both sides of this particular equality, I end up with x squared plus 1 to the 10th equal to the antiderivative of 10 x squared plus 1 to the 9th, 2x. And what I need you to focus on, again, is nothing more than 10u to the 9th, u prime appearing in front of you. So what we're going to see is a rule that will enable us to rewrite the integrand in a form that is easier for us to antidifferentiate. So let's begin. Let's choose a function for u. That will be our first step. Take the differential of each side of the equation. Balance the integral, and in so doing, account for the whole integrand. Substitute back into the actual integral, creating an integral that's easier to antidifferentiate, and then back substituting, going back to the original variable. Sound confusing? That's really the same sequences of steps over and over. Let's evaluate this integral. First thing I'll do is I'll choose a function for u. That means I need my inner function. My inner function will be what's raised to the 5th. U is x squared plus 11. Take the differential of each side. Du would be the derivative of x squared plus 11, that's 2x, dx. Balance the integral. What we mean is you have to account for the whole integral. X squared plus 11 will be replaced with u. What's left in the integral? 6x dx. I have 2x dx. So I'm going to multiply both sides of that equality by 3 so that my 6x dx will be replaced with 3 du. So if I may, just off to the side here, I will replace the 6x dx with 3 du. You can see the new integral that's now been formed. So let us substitute back u and 3 du into our original integral, which was 6x times x squared plus 11 to the 5th dx. And we end up with 3u to the 5th du. Again, 3 du are the double lines that we have here. U to the 5th is in place of x squared plus 11. We've created an integral, 3u to the 5th du, that's easier to antidifferentiate. So let's simply do so. Take the antiderivative. 3 times 1 over 5 plus 1, u to the 5 plus 1 plus k. Or 3 times the 6th, u to the 6 plus k. Now, we've antidifferentiated, but we want to write the antiderivative in terms of the original independent variable x. So we back substitute, replacing u with x squared plus 11, and at the same time allowing us to multiply 3 times the sixth, and we end up with a half. These problems are checkable. Now, to check, we simply differentiate. So if I differentiate 1/2 x squared plus 11 to the sixth, I have 1/2. I bring the 6 out front, take the inner function to the 1 less power, times the derivative of the inner function. 2's cancel, and notice that I have 6x times x squared plus 11 to the fifth times x squared plus 11 to the fifth, the original function in the integrand. All of these problems will be checkable. Let's evaluate the integral, 25e to the 0.5x dx. We're looking again for an inner function for u. So let's choose a function for u. I need you to see this particular integral as a composite function, and we have 25e to the u du is our goal. So u would be 0.5x. Once you choose u, you've created a forced move like in a game of chess. You will take the differential of each side based on what u is. So du is 0.5 dx. Then what do? Balance the integral. What this means is that I will replace 0.5x, so I'll underline that, with a u. That gives me my e to the u. But I also have to account for 25 dx. So we will multiply both sides of the equation by 50 and substitute back into the original expression. 25e to the 0.5x dx we replace with the integral 50e to the u du, creating an integral that's easier to antidifferentiate. Antidifferentiating 50e to the u is 50e to the u plus k. Back substituting to get the original variable x into the antiderivative, we replace u with 0.5x. Checkable? No, absolutely. Differentiate 50e to the 0.5x plus c. Take the 0.5, bring it out front, and you end up with 25e to the 0.5x. A third problem, again, we're going to evaluate an integral, and I need to choose a u. But for the first time, this is not quite as straightforward. If I may, I'm just going to go back a slide. My choice of u was the exponent on e. Go back a slide. And my choice of u, a moment ago, was what was raised to the fifth. Now, forgive me, but I'm just going to come back to the slide I'm at and say that I have two functions that are staring me in the face, 1 over x and 1 over x squared, and even a third function, x squared, that a student may think, well, gee, which would be the best choice for you? But if I can look at this integral and think I'd like to antidifferentiate e to the u, my choice becomes this exponent again. U would be 1 over x. Now, if I can account for the whole integral when balancing, then this is the right choice. But can I? Well, I will choose a function for u as being 1 over x. Let me see what happens when I take the differential of each side. Swing the exponent of a negative 1 out front, go to the 1 less power. Du becomes negative 1 over x squared dx. I take a look at my original integrand. 1 over x squared dx is what I have, but then I also have this multiplier over 4. Well, that's easily correctable. To balance the integral, I will multiply both sides by -4. So let us go ahead and substitute back into the original integral. 4e to the 1 over x squared. I'll replace 1 over x with u. I will replace 4 over x squared dx with -4 du. And I end up with an integral that I can easily antidifferentiate. I can antidifferentiate -4e to the u. I get -4e to the u plus a constant. And when I back substitute, I'll replace u with what u was initially, which was 1 over x. Now notice a small notational convenience we employ. When we switch variables from u to x, we change the constant because we were in the uy plane. We've now moved to the xy plane. Constant would be not necessarily the same. One more problem. Let's evaluate this integral. I need you to look at the integral and think to yourself, do I see a function u? And when I take the differential of each side, the end of the sentence would be, do I see its derivative? A give or take a constant multiple of it. Do I see a function embedded in this particular integrand? And do I see its derivative, give or take a multiple of its? So I choose a function for u. I'll let u be the inner function x squared plus x. Take the differential of both sides. Du would be 2x plus 1 dx. So for the moment, I will replace x squared plus 1 with u. And my 2x plus 1 dx, I need to transform into 10x plus 5 dx. What will I multiply to both sides of the equation? That will lead me to balance the integral. So I multiply both sides of the equation by 5. 5 du is equal to 5 times 2x plus 1 dx. That would be 10x plus 5 dx. And now I will substitute. My original integral, 10x plus 5 over the square root of x squared plus x, could be rewritten as 10x plus 5 over x squared plus x to the 1/2. I will take out the 10x plus 5 dx, replace it with the 5 du. I will take out the u and replace it. Sorry, I will take out the x squared plus x and replace it with the u. And can you picture the new integral? 5 u to the minus 1/2 du. That we can antidifferentiate. So let's antidifferentiate it. 5 over n plus 1 u to the n plus 1 plus a constant. And then we have 5 over 1/2, so we'll write that as 10. Replace u with x squared plus x. Raise it to the negative 1/2 plus 1. Well, that's 1/2 plus c. Thank you.